In this video, we're going to learn how to add and subtract radical expressions. Now, in order to add or subtract radical expressions, the two radical terms need to have matching indices, and the radicands, the expression underneath the radical, need to be matching as well. If this is the case, you can just add their coefficients together and get one radical. So for all these problems, we're going to simplify if possible. If it's not possible, we'll just put that it's not possible. Now here we have 3 square roots of 5x minus 2 square roots of 5x. Now the radicals are both square roots and the radicands are both 5x, so these can be combined into 3 minus 2 times the square root of 5x. 3 minus 2 is 1, so we just end up with the square root of 5x. In the next example, I have 6x squared square roots of 7 plus 4x square roots of 5. In this case, they're both square roots, but the radicands, the 7 and the 5, do not match, so these are not able to combine. So say it's not possible to simplify any further. Next example down here, we have 17 square roots of 3x squared minus 15 square roots of 3x squared. Now they're both square roots, so their indices match, and their radicands also match because they're both 3x squared, so we can combine these two. We'll end up having 17 minus 15 square roots of 3x squared. 17 minus 15 is 2 square roots of 3x squared. But now we're left with an x squared underneath the radical still, which can further be simplified by taking it out of the radical. Now, right now, the expression underneath the radical is always positive. So when I factor out a square root, I'll have now x on the outside of the square root because it matches the index, square roots of 3. But that x that comes out needs to always be positive because right now I could have a negative x value, but I don't want that to happen, so I'm going to put this in absolute value bars to maintain that this expression will always be positive. Next example, we have 3x square roots of xy plus 4x square roots of xy. They're both square roots. Their indices match because they're 2 and 2, and then the radicands xy are the same in each, so we can combine these. We'll now have 3x plus 4x times the square root of xy. 3x plus 4x is 7x. They are like terms. Square roots of xy. Now, neither x nor y is a perfect square, like we saw down here, so we can't simplify any further. That is where we stop. Next up, we have 12 cube roots of 7xy minus 8 fifth roots of 7xy. Now, while the radicands are matching, the fact that the indices are not matching means that we cannot combine these any further. So this is not possible, because the indices, the 3 and the 5, do not match. Now next up we have 5 square roots of 12 plus the square root of 12. Now these are both square roots, so the index of each is 2, so it matches. And the radicands are both 12, so I can't combine them further. So I'll have 5 plus an understood 1 in front of that radical. So I'll have 5 plus 1 square roots of 12, giving me 6 square roots of 12. And I can see here, just like I saw x squared earlier, here there is a perfect square within 12. Because 12 could be written as 3 times 4, and 4 can be 2 times 2. So multiplying all the prime factors, I have 2 squared times 3. So this can also be written as 6 times the square root of 2 squared times 3. And there's my perfect square underneath the square root. So I can take out a 2, give me 6 times 2 square roots of 3, which gives me 12 square roots of 3. So whenever you can simplify a radical, even after you combine them, you should. Now next up we have square root of 12 plus the square root of 75 minus the square root of 3. Now initially looking at all of these, they cannot be combined because all of the radicands are different. Even though they're all square roots, the numbers underneath them are not the same. But just like we saw down here with the square root of 12, we could actually simplify the square root of 12 before we start adding them together. The square root of 12, also known as 4 times 3, can be rewritten as 2 square roots of 3. Now 75 also has a perfect square in it. That's 25 times 3. The square root of 25 is 5. So we have 5 square roots of 3 when we simplify the square roots of 75. And the square root of 3 does not have any more perfect squares in it, so I'll just carry that down. But now we'll see here we have 3 terms, and they all have the same index, and now that all the radicals have the same radicand, now that I've simplified. So what I can do is combine them all now, and that gives me 2 plus 5 minus 1 square roots of 3, which is 7 minus 1, give me 6 square roots of 3. So sometimes initially you can't combine them, but once you simplify, you can notice that they can all be combined. Now, as I'm doing this cube root, I may not be as familiar with my perfect cubes, so I can look at the prime factorizations of each number. Starting with 250, that can be written as 25 times 10. 25 can be 5 times 5, and 10 can be 5 times 2. So there are 3 5s and 1 2 in its prime factorization, meaning this can be rewritten as 2 times 5 cubed. I'm doing a very similar thing I did the previous example, looking for now perfect cubes, and I've happened to have found one. We have 5 cubed within 250, so the cube root of 250 can be written as 5 cube roots of 2. Now 54, we can look at its prime factorization. 54 is 6 times 9, 6 is 2 times 3, and 9 is 3 times 3. So we have 2 times 3 cubed for 54. And we can see here we have another perfect cube. So I can take the cube root of 3 cubed, giving me 3 cube roots of 2, which again, I could simplify what I had before. Because again, there is no radicand that matches, but now as I simplify them, I can see, oh, now they have a radicand that can match, which means in my further step after this one, I can combine these two radicals. But now 16 can also be broken down into 4 times 4, and each 4 can be broken down into 2 times 2, giving me a prime factorization of 2 to the 4th. And here I do have at least one set of 3 of these 2's, like 1 2 to the 3rd. So 1 2 can come out, and another way you can think about that is like division. How many times does 3 go into 4? Well, it goes in there once, so 1 2 can come out. But I'll be left with a remainder of 1 2 on the inside, because 3 goes into 4 once with a remainder of 1. But now that I've simplified all of these radicals, now that I see that all the radicands can match, I can combine them into one. So 5 plus 3 minus 2 cube roots of 2. So that's 8 minus 2, which is 6 cube roots of 2. And that is how you add and subtract radical expressions.